Hi, in this video we're going to look at how to code the best first search algorithm for Godot. So it's basically ways of navigating. So navigating from the center square, this algorithm will do it for you. You've got a lot of choice for algorithms that do pathfinding. The main three choices are A-star pathfinding, breadth first search, and best first search. A-star for me took quite a while to set up for this kind of size grid. I basically a second of setup time when I wanted to connect all my nodes together. So that didn't work for me. Breadth first search is a bit inefficient. So this video, which I'll link to, explains how to do breadth first search. And basically what it does, you just sprawl out on all directions until you finally find your goal. And you can cursor it back to your current location. And to me that's a bit foolish, because if when I head to here, my first search would be down here, as that's the way that gets me closest to my goal. Both these will take me further away. So in best first search, you try and head towards your goal when at all possible. If you want a good overview of these algorithms, I'll link to another video that basically compares A-star, breadth, and best all together, and you see which one works best. I should also mention that Godot comes with a built-in navigation 2D node that can work for this kind of stuff. I did try it, however, ran into the problem. They have to have your navigation zone set up perfectly. In one of my code throughs, I had the hexagons not the exact size, possibly slightly squished from one the other, and the whole code just basically fell apart. So for me that was really fragile, I wasn't too ideal using it, and of course I had no control over what I could change and what I couldn't. So in this video, we're going to go through this best first search algorithm. So say we have a goal which is here. Every single step is going to look at each of the 6 neighbouring squares around my current location. Straight away, we're going to ignore any that we know to be obstacles. For each of the rest, we're going to calculate the distance from that square to my goal. And we're going to just look for the shortest distance. In this case, we've got 2 options. So we can see that these were both only 2 squares away. And we'll then pick one at random. Let's say we then pick this square. We then move our ship to this square. And then repeat it. We're also going to keep a log of all the squares we visited. So these squares have both been visited, so we can't go to them again. We're then going to repeat the algorithm from this square here. Again, we look at the 6 neighbouring squares. We ignore any that are either an obstacle or we have previously visited. And from the remaining 3, we see what is the distance from that square to my goal. In this case, the shortest one is here. So we then go to this square and then finally to my goal. Let's just see a slightly more complicated example. Let's say again, I had a goal and I wanted to go over here. So my first step to get the closest distance of my 6 neighbouring squares will take me to here. So I'll label both of these as squares they've already been to. Now repeat it from this hex here, and we notice we have no available options. All available options are either blocked or already been there. In this case, we back up a square, and we're going to run it again from my first square. Notice we can't go to this square again, because it's in my list of squares I've already visited. From the remaining squares, my closest is then here, and then it takes me along the rest of the path to my goal. Those 2 cases, that is basically the best first choice algorithm. That's basically all it needs to do. For my algorithm, there's going to be one more thing to it. That's if I want to go to this square here in the bottom right. What the algorithm will do, it will say I have 2 choices. And which choice it picks basically depends on which order I write the vectors in. For my algorithm, it will always pick this choice first in case of a tie. So I will go to this square next. Then again, I have 2 choices that are the closest, here and here. And my algorithm will always go to the right in case it's a tie. So I'll go to this square next. And then we can see the algorithm will then take us around, in essence, the wrong way round. It'll take us too long. So we're going to have a special check that's going to look out for this. We're going to say if at any point there's a branching path, where we could have gone one of 2 options, which we had over here, once we finished it, we're then going to run that branching path. That will say, find the first time I branched, and we're going to run this as a new route and see how this works. We have one special case that on the list of cells I can't visit, we're going to include the next 2 cells from my old route, just to make sure it's not going to immediately funnel us back down the old route. We're then going to follow the algorithm until we get to the goal. In this case, we get there a lot quicker. And we'll also check to make sure this new path will never be the same length or longer than my old path, to stop it searching for error for a second path that we know is going to be worse. And that's going to be it. We're now going to code all those special cases. Okay, let's introduce the scene we're going to be starting off with. So what I've set up already in the tile map is a basic hex-based grid. To do this in Godot, if I zoom in over here, you should be able to see that this is sort of like a brick effect, where all my cells are half offset here. This code is set up in another video on my channel that I'll link to in the description as well. In this basic setup, we have these tiles here which we can move through, and these planets, except for Pluto, that will act as our obstacles. In my world code, all I've got is one input event. If I left click my mouse, it'll tell me to pathfind from wherever I click. In my tile, I've got a few things set up. First things first, I set it so my tile map is always centered at 0, 0. I've set up some overlay tiles, which I also call down here. So when I pick a path, I can put a tile onto it that appears vaguely transparent, just so we can see what route we're going to take. And here, again, explain more in my other video, there's a quick function that will find the cell I click. So here, because we've got hex tiles onto a square tile base, we need a few special cases for when I click down here and down here, that I mean this tile here. Okay, the first thing we're going to need is a distance metric. From our tile map, we're going to need to have some bit of code that basically say how far I am away from where I clicked, where I want to go. And then from that, we can use the algorithm that'll take us 1 square towards our goal, and that's how best first search works. If I click here, I'm going to try and get 1 square closer towards it, and so on and so forth. Okay, so to get this metric on this hex-based grid is really hard. The best way to do it I found online, which I'll link to as well, is this page here, and that involves us resizing our grid, as you can kind of see here. So, because Godot's tile map is based off a square-based grid, it looks something like this, where basically your zeros go sort of along this zigzag here. That's really hard to get a distance off, so as we just saw, we're going to shift it slightly. We're going to shift it so that all my zeros are along this line here. Okay, and again, all these are going to be 1 1s, 2 2s, 3 3s, and so on and so forth. This will make it a lot easier to work out. If we look at this briefly, the way we get our distance is typically we always take the biggest value. So all these squares have a distance of 2, with 2 exceptions. If the two numbers have the same sign, so here and here, we just add those together. So here, both these add up to 2, or minus 2, which gives the distance of 2 for all these squares. And the same happens for everything of radius 3. You can do the exact same thing. If the signs are different, you just take the biggest. So the biggest is always a 3, except where the signs are the same, where if you add together these two numbers, it will have an absolute value of 3. So we can now use this to get a distance metric together. So let's code that now. So we're going to add 3 functions now. I want one function to adjust the cell in the way you just saw me do it on that little animation. I want another function to unadjust it. That'll do the exact opposite. And then I want a third function that is going to be the distance metric. It's going to tell us how far apart 2 cells are. Okay, first to adjust the cell. This is a really straightforward one. All we need to say is get the input, and for its x value, we need to take off floor, which means round it down, half of the y value for the input. And then we're going to return that input. For unadjust cell, it's the exact same thing, except rather than a minus here, we have a plus. Next, for a distance metric, I'm going to have it so that it always assumes that what I'm passing through it, those cells have already been adjusted. So I have some variable called distance. That's going to be 0. I'm going to set up 2 things called dx and dy. That's just the difference in x and the difference in y. So they're described like so. As we just saw, we're going to say if the 2 signs are the same, then we need to add them together. So if sine x is sine dy, then we know the distance is going to be the absolute value of those 2 things added together. Else, if the signs are not the same, then we take the max value. Okay, and once we've done that, we can return the distance, and that is that bit of code done. So we can adjust the cells as we need to, and we can find the distance between any 2 points. And now we're going to start the pathfinding function. So function pathfind. All we're going to pass to this is the current mouse position. So again, if you saw on world in this code, whenever I left click my mouse button, it just says call the pathfind function and chuck in the mouse position. Okay, first thing we need to do is we can see in the ready function, I adjusted all my tile map. So I wanted to send it to 0, 0. straight away I need to undo that. Next I need to know what cell I've just clicked. So I'm going to have a variable called cell, and that's just going to find the cell of my mouse position. I'm also going to create a second variable called the adjusted cell, and that's just where it is on my adjusted cell map. Okay, and I'm also going to say that everything from here actually, I've got to check that I haven't clicked on an obstacle. So all the important stuff I tend to just store here. I want this bit of code here. So if get the cell that I have clicked, and if we look on my tile map, that is cell number 1 is there. So if I don't click cell number 1, then I can run this code. If I do, we'll just do nothing. Okay, let's add a few more things. We're going to have a variable called the current position. For my code, because I'm sort of running like an infinitely big map, I'm going to say where I start from will always be vector 0, 0. I need to know how far it is to my goal. So distance to goal, for that we can use my distance metric. My start position is my current position. And typically this will have to be adjusted, but it turns out if you adjust 0, 0, this stays at 0, 0. So this would normally be adjust cell current position, but here we can ignore that. And my end position is my adjusted cell. I'm also going to say what the shortest route is. So occasionally in my code I look for branching paths. However, there's no point to look for the branches path if I've got the shortest possible route. So if the distance to the goal, say I'm 3 squares away, that means I will cover 4 tiles. So I say my shortest route is 4. I'm also going to get a couple more that I'm going to use later on. I'm going to call a variable, it's going to be the list of cells checked. So every cell I look at, I want to say I've looked at this cell, now make sure I don't look at it again please. To start off with, the only cell I've looked at so far is the current position. I'm also going to call another variable called alternative routes. This is wherever I don't have a unique shortest distance. I want to say I could have gone this way, so just keep an eye on it, we might look at it later on. Because to me Godot prefers not mixing and matching booleans and vectors, I'm going to say if there's an alternative route, I'm just going to call it a blank vector. So I always start with a blank vector, so I know that will never be a valid alternative route. Okay, we're now going to run everything in a while loop. So while my distance to my goal is greater than 0, as in I haven't yet reached my goal, I want to do some pathfinding stuff. First things first, I'm going to say my current position, I want to have it adjusted. That's because basically all my pathfinding work is going to work in my adjusted space rather than Godot's real tile map space. What I'm going to do now, I'm going to run a new function that's going to find the next path, find the next step. So let's add that function down here. And I'll say the best place to go will be this direction. That's all it's going to tell us. For this, we are going to pass the current position. I also need to pass it my target position. And I'm also going to pass it the list of cells I've checked. So like, if I've checked a cell, I then don't want to have to go back there again. That stops it sort of going backwards and forwards. Okay, we're going to create it in a variable. I'm going to call that the closest square. It's not actually the closest square, but it stores all the information I need regarding that closest square. I'm going to test it with a few variables that I'll explain later as we need them. I'm also going to have a variable called already checked. That's basically going to tell us if we've already checked a certain square, as in it was in this list, so don't look at it again. We're going to have a temporary distance to say this path I picked, this random direction, is it taking me closer or further away from my goal? Is it the best option or not? And of course we need a next position. And again, I can start off the blank vector. Before I get any further, I need to give me my list of options. I can have a list of options of what directions I can go. If we go back to that animation, again, I have to look at my adjusted tile map again. My possible options, you can see here, they're all the different directions I can go in from 0, 0. So these are basically my 6 options. I'm going to write an array and it's going to contain these 6 vectors. That's my possible 6 options to go in at every single step. And again, for every place I'm on this grid, if I plus on each of these, they'll take you 1 square in each of the 6 directions. So let's add that in now. Okay, so that's done. We've got this array that contains 6 vectors. We'll mention now, if you're doing this for a square-based grid, you'd like it a tiny bit easier. You're going to need the 4 vectors in each of the 4 directions, left, right, up or down, or occasionally the 4 diagonals as well. And of course, because you're on a square-based grid, you basically get to ignore all this adjust and cell business. And for your distance metric, you would just do a Pythagorean distance of doing square root of a squared plus b squared. Okay, now in our find next step code, we want to look in each of those 6 directions. So we're going to say for I in the range of this thing here, so we need to call it size as well. So because it's got 6 variables, we'll loop through it 6 times. And we're going to say for each one, we're going to consider this next position. And the next position will be the current position plus the ith entry from that array. First, I'm going to do a couple of checks. I want a variable called next position unadjusted. And I'm going to check 2 things. I'm going to check 1, make sure that position is not an obstacle, so make sure to actually go there. And secondly, also check, have we already been there? Is it in my list of cells checked? I have 2 if loops. First if loop, we are going to check if I've already been there. So I'm going to say, if my next position unadjusted matches up with any of the current cells, then we know we can't go there. We can just say I've already checked that square, so don't check it again. We can also have a quick check as well to see whether or not that is a valid target. So again, in my current code, the only obstacle is tile number 1. Of course, that will change if we have more and more obstacles. For here, I'm also going to say that already checked is true, so I'm going to piggyback off this bit of code. Now we can say, if we can skip it, so if already checked is true, then don't do anything, except you will need to reset already checked to false. And then else, so in this case, we haven't already checked it, it's not an obstacle, so we can look at the cell and I'm going to see how close it is. So I have variable distance from the cell, and I'm going to use my distance metric there. Give me the distance from the start position, which in this case is my next position, and my end position is my target position. Again, this will always be adjusted cell, but I'll give another few options if we need to change it later on. We're then going to say, if this distance from the cell is less than the x variable of my closest square. So again, in each one of those x, y, and z, I'm going to store some information. I'll get to one at a time. So if it's the closest distance so far, we're going to store that distance, and we're also going to say where we found that information. I'm going to store that in the y variable, and I'm going to say that's just going to be I. So I was looking at that cell. We have another option here, and that's through the branching paths. So again, if I find the closest distance, that's great. However, what if I find the distance that's the same distance as my closest distance? So that could be worth checking out later on, in case we go like a left or right option. Do we go left, do we go right? This will handle that bit of code here. We're going to say, maybe it's not the shortest, but maybe it's the same. We're then going to say, let's store that as temporary distance. And we'll check at the end if that was actually shortest distance. I'm also doing a quick change. I think it makes slightly more sense to have this variable defined up here. I'm also going to store where this direction was. And I'm going to store that as a z variable. I'm going to say, in this direction, we had the same distance, so it could be a branching path, it could not be. Once you've run through this for loop, and we've gone for all our cells, we just want to quickly check this again. So we're going to say, if we found another option, so again, this always starts off set as -1, so if it's not -1, we just want to check that this temporary distance we found actually was the closest distance. Because again, it might have changed after a bit of code's run. So we're going to say, if it's not the closest distance, after I've checked all 6 cells, then just wipe it. Then we don't really care about it. And again, we're going to reset it to its initial value of -1. And these values are mostly arbitrary, but for me they kind of worked. Okay, that's the find next step code done. Once we've done all that, we just want to return the closest square. So that contains the distance it got me to. It also contains which direction I have to go in to get the distance, and any possible branching paths. It'll only return one branching path at a time, but a hex-based grid also you'd really tend to find. Okay, so we're going to go back to my pathfinding code, and we can add that in now. So we're going to say the closest square just equals this find next step code. And my target position will be my adjusted cell. And I cannot spell apparently. Okay, so we have an option here. It's possible that occasionally you won't return a closest square. you won't find anything. That's basically if you're completely hemmed in or you've checked all the squares that you possibly check. So you want to check here to say, make sure I actually found the square. So make sure it's not going to be infinity. We'll do that special case in a bit. We can now add in the next path. My next path is current position, and then we're going to see which direction it was in. All the directions are stored here in adjacent adjusted cells, and we want to go in the direction that we stored in the Y variable here. Worth mentioning, this next path will return it in the adjusted tile map. I want to unadjust that, so we're going to say unadjust that cell, please. Okay, so that's going to be the next square we're going to need to go in. We are also going to log if we found a possible branching path here as well. So again, if it's not its default value of -1, that means we found a possible branching path. And that stores an alternative routes. So we're going to pen that new value on. And that's basically going to be the exact same code here, except instead of picking the Y value, we're looking at the Z value. We're also going to tell it now that once you've finished going through this path, it's worth having a look at those those alternative routes. So I had a variable called alternative routes check, and we're going to say it's true. And that's going to tell us we found a possible alternative routes, just have a quick look at them. And that defaults as false. If not, that means we found no good alternative route. We are just going to add in a blank vector. Just want to make sure that my alternative route size is the exact same size as my list of cells checked, so they're easier to correlate together. So we add in a blank vector. Next, I need to upgrade my distance to my goal. That was stored in the X variable, the closest square. And I'm also going to update my current position. That is the next path. And we're going to add that path, or add that position, to my list of cells checked. Okay. Else, this is the case where we found no valid targets. All we're going to say is run the code again, but I want you to go back to the previous node. So -1 was the last node of the list, -2 is the last but one node. So in this case, it's going to say, if you got to the end, just back up one square, and then keep backing up one square until there's other options to go. So this bit of code now will now find you a path, keep looping through it until it finally gets you to the goal. We have a few special cases, or a few checks we need to do now. So if we look at the finished code just for a second, what's happening right now we need to check for is when I click this square here, the first thing I'm going to check is going to be this square here. Okay. Then I realise it's got stuck in there. I'll have to back up to my first square, and then I'll take a new square and actually work its way to the goal. What I need to say is when we actually display in this route, or this final route, we need to delete this square here. We need to say you can ignore that, it doesn't count. We're going to run that code through now. Now here, unfortunately, we can't use a for loop, because if I start removing stuff from it, I'm going to have basically too many items left in my list. So we're kind of stuck with a while loop. So we're going to say check will be my while loop. I'm also going to loop through II, so I don't use an I. I'm also going to log all my skip cells. So if I skip a cell into an alternative route, I want that alternative route not to go to that skipped cell. So we'll know that's going to be a dead end or something like that anyway. While we are checking, we need to first of all check if we are near the end of my cell. So we first of all need to check if we're somewhere near the end of my list of cells checked. So we're going to say if my list of my cells checked minus II. Once we get to the last couple of items, we know there's not going to be any sort of branch paths right near the end. So if that happens, we can just break out of my loop. If not, if still a few cells left to check, then we're going to see if we need to remove a cell. So we're going to say if the distance metric between my start position, which is the cell I'm currently looking at, and the cell that is 2 cells ahead, if that distance is 1, then we know we can skip out the cell in the middle. So we're then going to remove a tile. What I want to do first is I want to include that in my list of skip tiles. I want to say this tile was at a dead end, so we ever look at branching paths, we don't want to go there. So list of cell checks, that'll be I plus 1. We then go for my list of cells checks, and we're then going to remove that cell, and we're also going to remove it from my alternative routes. Just remember, this is basically a line in terms of size of my list of cells checked. Okay, so now we're going to skip out the branching paths. Double I's and declare, that's because it should all be double I's. Okay, what this code will now do, anywhere we had a sort of dead end to backtrack, we can now skip that out fairly nicely. The last thing to do, because we're in a while loop, we then need to manually iterate up I. And if you find something to remove, we then don't want to iterate I. We want to check again if there's something else to move it on top of that. Okay, now we can check it's working. We're now going to go through each of my items in my list of sales checked, because that represents my path. I'm going to say for each one of those, we want to lay a tile down. Okay, so that's now working. What I was going to say is that right at the start of this program, we want to remove any tiles that are laid down, because then we're going to have more tiles laid on top of each other. So we're going to say the first you want to do when we pathfind actually is remove all the children, because that's where I've stored all the paths. So remove child, and we want to get child 0. So when we move to the 0th child, then all the tiles will shift down into its place. On one slight correction, this will occasionally get false positives. That's because I haven't told it to adjust these cells. So both these cells we need to adjust because that's how the distance metric works. So now we have our basic pathfinding node done. Okay, this is the most basic case of best fit. We're going to have a few more things to it in a second, and that's going to be looking for branching paths mentioned a few times so far. So if I go down this path, by default it always checks going to the right first. So it would rather go this way than look at going down. We're going to say now, hang on now, we have this as an alternate option, so let's check if this route was quicker. Which here we can see it is. We're now going to make the code look for that route and see whether it's worthwhile. But aside from that, this is basically best fit. Doesn't always work the best it can, so again here, we should be going down and around, so we need to look for branching paths, as we should here. Okay, so first we're going to say is, do we have an alternative routes check? So again up here we said, if we put in alternative routes, we put that check as true. We're also going to say that in order to look for alternative routes, we must not have found the shortest route. So ages ago we stored something called the shortest route, the shortest possible routes, and we're going to say that cannot be the number of sales checked. So list of sales checked.size is the length of my route. So we're going to say if we saw alternative routes for a possibility, and we haven't found the shortest route possible, we then need to search for alternative routes. In a variable which says check for alternate routes, it will only stay true if we have found a shorter route. So if we look for all my shorter routes we couldn't find one, it will just default to false. If we found a shorter route, we then want to check again to see if there's an even shorter route. So while we're checking for alternative routes, first thing we're going to do, we're going to set that to be false. If we then find a route, we'll then reset it to be true, so we can then look for another route. Okay, again, what I said earlier, you will never find an alternative route right near the end, so we don't need to check the last couple of variables. We then said that if the alternative route, if there wasn't one, we just said let's call it a blank vector2. The reason I did this was I found it hard merging vectors and balls together, so it's had as a blank vector2 is like my null case. Okay, what we're then going to say, if I quickly just run my code, when you pick an alternative route, if you're going down here, we don't want it to go back on the route we've already tread upon. So here we had our first branching path. We could go there, we could have gone there. We're now going to say go with this new path, however, say these cells are here have been checked. Say you've already looked at them, so then we don't go down that old path again, just in a more inefficient fashion, because that will never work. So we're going to say we're going to have an alternative list of tiles checked. So it's going to say as my list of tiles checked, but I only want the first few values. I don't want all of them. To do that, we have to use the slice code. We want to begin at 0. We want to have the next 2, which takes us up to j plus 1. And I want 1 and false. No idea what the false means. The 1, sorry, that should be an I. The 1 means go up every tile as opposed to go up every 2 tiles, every 3 tiles. At the end, we then need to say you need to remove those tiles if we find a quicker route. Next, we stored a variable that was called skip cells. That stored any cells that we have to move because our dead ends. we want to include others in as well. So we don't want to go back down dead end route. So we can add that to my alternate list of tiles checked. And if we've done that, we need to then log on. I have one more tile to remove. Okay, we're also going to have a new current position. We're going to say now restart it from the last tile. Will always be I-1. We're then going to rework out the distance to the goal. That's going to distance metric. That's going to be the current position. But we need to adjust that cell first. So adjust the current position. And we're going to our angle, which is adjusted cell. We've got a couple of things here. We're going to add the old length of my old path. The reason we're doing this is because if at any point I've gone longer than my old length, I can just stop. I don't want to keep searching forever to find a more worse route. We'll also store the new length. That is just going to be I. Okay, we're then going to run a similar bit of code to what we had in our original pathfinding thing. And do something similar to this. We're going to say, well, the distance to the goal is greater than 0. So we've still got some distance to go. And we must have our new length being shorter than our old length. We're going to say old length -1, so I don't even want it to tie. I want it always to be better. Okay, when similar code to before, current position, just adjust that cell. And similar lines to before we had in our first code. So I'm just going to copy all this down, but I'm going to change it quite heavily. So copy those down, most of this we can keep. We can delete this check. What I do want to say is we do want to install the alternative routes. However, we of course need a new variable. If I keep appending it, it'll just add more and more things to the end, which is going to be what we want. So we're going to add a new variable up here that slices it the exact same way we slice the list of cells checked. So here I don't need those extra two variables. I can stop where the new path starts. So this is an alternate list of alternative routes. If we then find a shorter path, we will then call this variable the new alternative routes. Okay, let's make a couple of changes to this. So these have been renamed. Distance to goal is still fine. Current position is still fine. I'm now going to add stuff on to my alternate list of tiles instead. And I also want to say this new length is now 1 bigger. So I've looked at another tile. We don't want to go too far. If at any point we find a dead end, I'm going to say we might as well just give up. We're never going to find a dead end and then find a shorter path. Here I can just break out of the while loop. You could also say new length is infinite if you want to, but I think break's a bit of a key. Okay, so now we finished the while loop. We're going to see if we found a better route. Because what happened here, either we got to our goal, we found a dead end, or we went longer than our previous length. If we got to our goal, if that was the reason this while loop ended, we then want to log that new route. What I'm going to say straight away is I want to check again. I want to check for that new route. Was there a new alternative route that could be even better than the first route? Next we can do, we can remove these skip cells and these extra routes I chucked in there. Find the range of tiles to remove. I just want to remove the ith tile. So alternative list of tiles checked. Can you please remove the ith tile this many times? So if there were 2 tiles to move, it would move that tile twice. I'm also going to say, we then need to say alternative routes is now the alternate list of alternative routes, which is the one we'd been added onto here instead. And then if we found a shorter route, we can break out of this for loop where we checked all the alternative routes. Otherwise we'll keep checking through them. So last we need to do here, if we found a shorter route we haven't done yet, we need to then rewrite the list of cells checked. What I wanted to do back up here when we called the closest square variable, I think I told it to ignore the list of cells checked. But of course now it's running through the alternate list instead. So if we change that, then that's pretty much the pathfinding done for the basic case. Now we'll search for alternative routes where possible. What I'm going to do now, I'm going to see how I can break this. I just want to make my code as robust as possible. So I'm going to quickly change the trial map to give it a couple of new challenges. First challenge we're going to look at is when we've got basically a double hole here. And so far my code doesn't handle that well, so we're going to change that adjustments now. If we run that bit of code, it'll get stuck in an infinite loop, and that's because of this line here. This is the code where if there's no squares we can go to, we go back to the last square. However, if there's no squares we can find twice in a row, it doesn't go back twice. You basically get stuck on the last but one cell. So we can have a new variable. We'll just call that count back for now. And that would be -2. And every time we call this function, we want to make count back one smaller. So next it'll be -3. That means I'm going to keep backing up one cell at a time until there is a valid path I can take. Okay, so that code now handles that double hole before it would loop infinitely around here. What I notice now is I'm not correctly reducing the squares that I don't need. So this square, this square, and this square should all be taken off my path. Also, there's an edge case where if I've got sort of 2 corners, my count back will suddenly get too big. So if we do find a successful route, I want to reset that count back to -2. Otherwise, I might suddenly back up 5 squares if it's the second corner I get myself stuck into. Now, we're going to make a few changes here. And that's basically to do with this skip cell function here. I'm going to basically bring it a bit higher up. What I'm going to say is, whenever I get into this case where I basically trap myself into a corner, I know that whenever I back up, I can basically skip all those cells I've had to back up to. So we're going to add a new variable, and we'll call this the final path. And that'll start just the same as list of cells checked. In fact, it'll be exactly the same as list of cells checked, unless I get myself stuck into a corner. That is going to add a line here. That's the same for my final path. Remove that last entry. Okay, also, like I said, I'm now going to move skip cells up here, which means I need to copy this line here, or cut and paste. Okay, and here we just want to add the entry that I've just removed, which is stored under -1. Again, make sure this runs before we remove that. So what we're going to do now is when it's stuck into dead end, I'm going to log those cells that were the dead end. They will be in skip cells. We never go down that path again when we search for an alternative route. We're going to move that from my final path. This check is fine now, so we don't have to worry about that anymore. And when we do this alternative list check and stuff, basically everywhere we've got list of cells checked, we're instead going to use the final path variable. And same thing here, this check should only work for final path rather than list of cells checked. Okay, and here I've got to make sure my alternative routes is now synced in with my final path. So I'm also going to want to remove the same node from alternative routes. Again, these two nodes will always be the same size, that bit of code is going to be fine. So going back through this code, make sure that all the list of cells checks are now final paths. And we're going to run that same bit of code here as well. Okay, all the functions are absolutely fine as they are. Here we're going to make a slight change. In my will function, I'm just running this. I'm going to now want it to return the path that I'm going to later want to take. Also, I'm going to pass a current start position. For that, I can just use the ship or my sprite. Okay, so now it's going to find a path between the sprite's current position and the global mouse position. And again, we can quickly update that at the start of the find path function. So I'll pass that through the current position. This line can go, and we basically want these same 2 lines here, but for the current position. Okay, now we need to create this path variable. So we can start as an empty variable. Every time we lay a tile, we're going to say add that to the path function as well. So it's not just going to be the same thing as the final path, because this will just be the cell and I want the actual in-game coordinate. So we're going to say map to world of final path I. And once we've done that, okay, this will crash. That's because I very foolishly haven't copied this line down for final path. So now that should be working. Okay, it's the same job, but now we don't crash in this case here before we had an infinite loop. I'm going to cover one more edge case here, and that's going to be where we basically stuck in a hole and I try and click out of the hole. So right now, again, I'm at 0, 0, so clicking here, everything's fine. But if I click out of it, we're hitting a crash, and we're going to change that now. So to solve that problem, we're going to have to check here to make sure that this final path size is never 0. So if it is 0, we know for a massive problem that in fact we've got nowhere else to check. Okay, turns out all we need to do here is just break out of this while loop. The basic code will handle all of that. You could have separate if loops saying if the final path size is 0, skip all this stuff. But it's such a rare case, I'm not going to worry too much about that. So the last couple of changes with a bit more robust code, that hopefully covers a few more edge cases. Again, personally, in this game wasn't going to be a massive issue, but it's all going to check that your code can handle any awkwardness it might possibly be thrown at. Let's try and click a quick maze and see how well it actually handles it. Okay, let's make one more quick improvement. So again, run on this maze. If I click here, we get this extra square here. That's because in alternative routes check, we don't run this bit of code, which checks if I can do a quick shortcut. So we're going to bundle this in as a function. I'm also going to change it quickly. Because I break out of this loop, the fact that I've got a variable check here is kind of useless. So I can just say while true here instead. So let's cut this out, and let's make it a function. Let's just call it shortcut check. Okay, for that new shortcut check function to work, so we need to define these as variables outside the function. Now with that change done, the function shortcut check should now be working. And we can see we're handling these set of mazes fairly well, without anything going too horrendously wrong. Okay, I hope you found that useful. If you want to see more in depth of how to get a ship moving, or basically using this path, then please follow the other half of the tutorial, which is all about making a hex-based strategy game. Otherwise, thank you for listening.